Okay, now we're going to see part two of cache organization. Part two. Um, let's start with a general organization. Okay, so as I said before, the cache has a certain number of sets. That's where data can go, and each set has a certain number of lines or blocks. By the way, line or blocks, cache block or cache line mean the same thing. Okay, I might use them interchangeably. So a set has a number of lines, which is the same thing as the way. If I say a cache is a four-way associative, it means that we're going to have 1, 2, 3, 4 lines in a set. Okay. So when a cache has two to the S sets and 2 to the E lines. Okay. So now in each line in the cache has a bit of metadata, right? The first one is the tag that we saw in the previous video, right? The tag encodes, stores the rest of the address that cannot be figured out just with the set alone, okay? So we know what data was stored in that block of the cache. There's also a valid bit here. The valid bit is used to determine whether the data stored here, stored in the data part of the cache, is valid or not. For example, when the cache starts up, it starts up empty. So if there's some random addresses there, we don't do that to get confused with with valid data. So this valid bit is all set to 0. This valid bit is also used in the context of multi-cores, when we might have to invalidate data when there's remote updates, but this is the subject of a more advanced computer architecture class. But the valid bit is also used in the context of multiprocessors. Finally, so there's 2 to the B bytes in a cache line. Okay, so the reason we're using powers of 2 here is such that it'll be easier to figure out how many bits we're going to need for the address. Okay, and a cache line, so a cache block here in our example is has as many bytes as the value of this B variable here. So that means that the cache size is S, which is the total number of sets, multiplied by the number of ways, or the number of lines per set, multiplied by the size of the block, capital B. Let's see how a cache read works now. There's multiple steps in a cache read. When the processor sends an address to the cache to be looked up, the first thing the cache has to do is locate the set where the data goes. Okay? So remember that we saw in the previous example determining where the data goes. We saw that there's some bits of the address that are used to determine in which sets the data goes. Okay? And those bits are here in the middle, right? So we're going to have S bits, because if I have 2 to the S, little s sets, I'm going to use little s bits as the set index. Okay, so I'm going to use that part of the address as an index to the cache, which is, so if this is 0, 1, 2, until s minus 1, and we use that value to determine which set here we're going to choose. Okay. Once we do that, what we're going to do is we're going to see whether the tag of the address, the t bits, the upper part of the address, matches the tag stored in the block. And okay, so that's what we're going to do. Now, and then we're going to use the lower part of the address, the block offset, to determine which part of the block we are going to read, because, as I said, a cache block or a cache line can be 16, 32, 64 bytes, but often we read one register's worth of data, which could be 4 or 8 bytes, or maybe 1 byte only, so you have to get only part of the block. Okay, so let's see now how this works. I'm going to show how this works for a direct mapped cache. Okay, with a direct mapped cache, there's a single block per set. Okay, so what we're going to do is we start with our address. Okay, so we're going to get find the set. Okay, so it happens to be 0001 here, so it's probably 0 and 1. And we know that we're interested in this line here. What is the next step? Well, the next step is to read that, select that line, and then determines whether the tag matches. Okay, if the T bit, the upper part of the address, matches the tag stored in the cache, if it matches, we have a hit. If it doesn't match, we have a miss. Okay? So the next step, and so if it matches and the bit is valid, we have a hit. Okay, if either one of these is not true, if it's either not valid or it's not a match, it's going to be a miss. Okay, so now let's assume that the cache block size is 8 bytes, which means that now here we have 8 bytes. Okay, so now depending on what's going to happen, we're going to use the block offsets to determine that happens to be 1000. We're interested in this part of the address, so that's what we're going to read. So these are the 4 bytes that are going to be read in this example. Okay, great. So now, if there's no match, if it's a cache miss, what's going to happen? The old line, whatever was here, is going to be scraped away. It's going to be thrown away, and the data that comes back from memory is going to come back and replace the data that was there. Okay, now we know how reads work on direct mapped cache. Let's see how reads work on a set associative cache. Okay, in a generic E-way set associative cache. Okay, and in our example here, let's make E equals 2. It means that it's a 2-way set associative cache. That means I have 2 lines per set. Now I have 2 lines per set. Okay. What is the first thing we're going to do? Again, we're going to use the middle part of the address to find which set it goes. Let's say that it goes again to set 1. But now what we're going to do, we're going to select this set here. Now we are focusing on 2 lines. Now that means that the data here can go in 2 places in the cache. So the comparison with the T bits of the address with the tags now has to involve 2 values. Now we're doing 2 comparisons. Okay? So, and then we're going to do the same thing. If either one of them is valid and has a match, then we have a hit. Could be neither one of them. Of course, we're not going to have both of them, otherwise there's a bug in your cache. It should be either one or the other, but not in both. Okay, so it should be a match in only of them. But if both of them have a miss, they either don't match or the bit is invalid, the valid bit is set to 0, then it's a cache miss. Okay, so let's say that we determine that this is a hit. So now the same thing, we're going to get the data. So now it just we happen to do a 2-byte, we do short int, right? Reading only 2 bytes. That's where the offset starts. We're going to get these 2 bytes here, read it, and send it to the processor. Okay. So if there's no match, one of those is selected for eviction and replaced. As I said before, we normally use this policy called least recently used. Okay. Now let's look at types of cache misses. There are many types of cache misses. Okay. There's 3 types, not many, 3 types. Okay, that's what we call the 3 C's of cache misses. There's actually a 4th one when we say multiprocessors, but so that might be for another time. The first type of miss is called code miss or compulsory miss. That's a miss. There's nothing you can do about it. So it's a code miss. The first time you access the data, we haven't seen it before, so it's a miss. That's the first time you see the data. In fact, I lied. It's not that you cannot do anything about it. There's some techniques called prefetching that can reduce that. But typically a code miss is hard to avoid, and just because the first time you access a block. Now a conflict miss is a miss that happens just because of the cache organization. When you have multiple addresses that map into the same set, one could kick the other one out. When that happens, you're during conflict. Okay, conflict is normally not a good thing. And in the case of caches here, they just kick each other out. Kick each other out, so that's going to reduce the effectiveness of your cache. Okay, so for example, if it's just one, if it's a direct mapped cache, you have more conflict misses. As you increase the set associativity, the number of ways in your cache, okay, you're going to have a lower conflict miss because there will be fewer cases where data will kick other useful data out. Okay, so conflict misses happen when cache is large enough, but multiple data objects map to the same slot. Okay, great. Now the final type of cache miss is a capacity miss. A capacity miss just means that the amount of data that you cycle through, that you access repeatedly, which is called the working set data, is larger than the cache. So fundamentally, you'll be kicking things out. Okay? So one way to think about conflict misses is, by the way, if you increase the associativity and the miss will go away, it's because there was a conflict miss. Okay? So far we have talked only about reads, but writes are very important too. Okay? And the most important thing about writes is that the data might occur in multiple places. Okay, so if I have, for example, I have my CPU, then I have my L1 cache, L2 cache, and so on. If I access a certain piece of data A here from the CPU, the data is going to be stored in the L1 eventually and the L2 as well. Now, but this is when I'm reading A. But what happens when I say I now write to A? If I write only here, I'm going to disagree what's here, and vice versa. Okay, so the main problem is that the copies of the same data spread over the caches in the hierarchy might disagree with each other. That's not a good thing. Disagreement is not a good thing. Okay, so so what to do in a write hit? That's an important question. There's two basic policies. One's called write through, which that means that if I say I have my CPU here and I have an L1 cache, and then here in our example, say that in this example, say they have memory. When a processor says write A, so the CPU sends data straight to memory. It might have to update whatever is in the L1 cache, but it sends data always to memory. And the bad thing about that is that every time the CPU writes to something, it has to always go to memory, even if it's in the cache, right? So because it's in the cache, you do both. You write through immediately write it to memory, updating the cache. Okay. Now, write back works as follows. This is write through. With write back, when the CPU writes to A here, it just writes to the cache, and now there's a little bit here that gets set that says, okay, this data is now dirty. It means that the copy in memory might not be the same. So whenever this line is displaced, it's kicked out of the cache, it goes and sends the data to memory. Okay, so we need a dirty bit to indicate the line is different. Okay? So now this is what we do in a write hit. But to do in a write miss, you have two options. One is called write allocate. In other words, should we load the data in the cache first and then do the write? Or, and that's good because if you're going to write and then do more writes, that's a good thing because we allocated the data. Okay. Now, the other option is no write allocate. So you just write, if it's a miss, you just write to memory, you don't do anything to the caches. Okay. And another way that write allocate is useful too is if you do a read, if you do a write that's later you're going to do a read, that's a good thing because it's likely to be in the cache. So typical caches are either write back with write allocate. Usually that's a common case, although write through and no write allocate, occasionally you see that, especially in some machines that have multiple processors. To end this video, let's revisit the Core i7 cache hierarchy. Okay? Remember that I showed you there were multiple L1 caches, L2 caches, and there's an L3 cache shared by all of the cores. But now we can understand some of the other data here. When I said that the L1 is A2A set associative, okay, that means that both the L1, the data L1 and the instruction L1, the D cache and I cache, are both set associative. They're not direct mapped. And that's a pretty high associativity, right? Because the designers decided that it was worth throwing the complexity to reduce the type of misses, and to reduce conflict misses. Okay? Now, the L2 unified cache, and by the way, the L1 cache is 32 kilobytes each. The L2 cache is 8 times bigger, and it's also A2A associative. And notice that the access time of the L1 is 4 cycles, the access time of the L2 is 11 cycles. Okay? Now, the L3 is already much bigger. We're talking about 8 megabytes, and even higher associativity to have even lower conflict misses. And that's because the access time is also much slower than the L2. But the reason that the L3 also has much higher associativity is you want to reduce the misses. When you reach the L3, you better hit, because if you don't, you have to go to memory, which is much more expensive. Okay, and the block size here is 64 bytes in all cases. Okay, see you soon.